Hi everyone, welcome to the second physics transition lesson for John Taylor High School for this year. The quote on the screen is a quote from ancient Greek philosopher called Democritus, who was one of the first that we know of to hypothesize anything around atoms, simply saying that the only existing things are atoms and empty space. That's quite a sobering thought if you think about it, particularly if you consider how much of us or anything is actually empty space. We will look at that when we're back in school. We know now that it's not quite the whole story, that ordinary matter would certainly be atoms and empty space, but we also are aware of a whole host of different particles, and that's the sort of thing we're going to start to delve into moving into the A-level studies. So the second lesson is going to be introducing particles and bridging the gap between what we did at GCSE, an introduction to some of the simple subatomic particles and some of the more advanced A-level calculations before we meet some of these new particle groups and different types of particles in next year's lessons. Just a quick overview. I'm not going to read through the entire slide, but how particle theory and atomic theory has developed. Considering Democritus said what he did in 400 BC, there wasn't an awful lot advanced on that until 1837, when John Dalton sort of came up with a very similar idea. Since then, though, there's been a very rapid, particularly in the last century, there's a huge amount of work done in this field and some very rapid advancements, and it is a field that is still very much at the forefront of physics today, and new particles being discovered and different ways and that they can be used and different things they can tell us about the world around us and even further the universe and how that formed. Some of these on here you'll be very familiar with. You will have heard of, for example, J.J. Thomson discovering the electron, the work of Ernest Rutherford, James Chadwick. Some of the other aspects will be different things. And what's quite interesting is sort of the interplay between some of the more modern ideas, things like consider quantum physics perhaps a very modern idea, but that was first formulated in 1900, 30 years before they actually discovered the neutron. So there's quite a few different aspects there to see how it all comes together. Another interesting aspect to consider here is that in most parts of science and particularly physics, there's been plenty of times where the theory is based on experiment. However, in this particular field, you'll see that as physics developed and as we got to more modern times, actually it's a theory that leads the experiment. The theory comes first and the experiment later. So it's actually a wholesale change in how science has been done. And you'll also start to see that as you move through, the number of names for each discovery or theory increases as people tended to work together more, and obviously more recently it's now not individuals but organisations that are doing the forefront of the work, with huge teams working together on this. So first of all, the quick recap. We know that the constituents of an atom will be proton, neutron, electron, and hopefully your introduction work before you've started this clip, you'll have reminded yourself of those. You will have a good understanding, I hope, of the relative charges and the relative masses that were part of GCSE. So a proton having a relative charge of 1, the electron -1, the neutron 0, and in terms of mass, proton and neutron both the same with a relative mass of 1, and the electron negligible. It's about 0.00055 if you're going to enough significant figures on that. But for A-level, one of the first things we've got to do is deal with actual absolute values rather than the relative values. So in terms of charge, we've got to look at the charge in coulombs. And you can see there, well, the proton and electron we know have the same charge, just opposite in one's positive, one's negative. So we've got a charge there, 1.6 times 10 to the power of -19 coulombs, positive for a proton, negative for an electron. It seems a bit of an unwieldy number to start with. It will be a number you become very familiar with throughout A-level studies. So that is an important reference point for you. Similarly on mass, a proton and neutron almost the same, but you can see if you go down to a fourth significant figure, the neutron is ever so slightly more massive. but both around the 1.67 times 10 to the minus 27 kilograms, which is considerably greater than the electron at 9.11 times 10 to the minus 31 kilograms. They're very small, but those differences actually can be quite significant in a lot of different areas. So those numbers are ones definitely to get used to using, and we will be using those a little later on in this session. Just another couple of revision points. These are really key, and again, hopefully you've already thought about these in the introduction work for this week. Knowing what an atomic number and a mass number are, and the definitions of isotopes and ions as well, which isn't on this particular slide. But these are really important definitions that you make sure you get your head round. Isotopes, just a really simple but very common exam question, define an isotope. So an atom of the same element with the same number of protons, but with different numbers of neutrons. And the notation you will see in the center there, you can see the sort of old-fashioned notation with the mass number and the atomic number and the elemental symbol. But you may see a different notation, which you will see on the worksheet itself, which might be just to give you the name of the element and the mass number only. The reason you can get away with that is because the atomic number defines the element. So if you know the name of the element, so elephant then, the element, you already know the atomic number. So for example, iron might be described as being iron 56, which means it has a mass number of 56. It might be described as being 58, so the mass number being 58. So you might see iron 56 or iron 58, so on. But because it's iron, it always has an atomic number of 26. So quite often that will just get left off because saying it's iron also tells you the atomic number is 26. It becomes important to sort of find your way a little bit around a periodic table to help with this. So the new concept we want you to have a little look at for this introductory lesson is the idea of specific charge. Specific charge is also known as the charge to mass ratio, which is therefore measured in coulombs per kilogram. Now the charge to mass ratio is just simply that, it is the charge divided by the mass of a particle. And the purpose of doing that is because there will be certain behaviours of the particle, particularly when placed in electrical magnetic fields, that are determined by both charge and mass. So perhaps the motion of the particle will be determined by this charge to mass ratio. It's a really key thing, and it's actually usually easier to measure the charge to mass ratio of a particle than it is to measure the charge or the mass independently as well. So the equation simply specific charge equals the charge Q divided by the mass M. And a little bit of trivia, but it does come up quite often on the exam as well. The electron actually has the highest charge to mass ratio of any particle, and you will be asked to calculate what that is on the worksheet in a moment. So I'm just going to take you through a couple of simple worked examples for how to do this, and we're going to look at calcium. So, first worked example, so to calculate the specific charge of a calcium-40 nucleus. Okay, so this is an example of what I was saying about the notation. You can see how it's written there. So with it being calcium, we don't need to write down the atomic number because all calcium nuclei have the same atomic number. It doesn't matter what the mass number is, they will all have an atomic number of 20. So there are 20 protons, so the charge on that nucleus is 20 multiplied by 1.6 times 10 to the minus 19. That's the charge on each proton. And that gives us a total of 3.2 times 10 to the minus 18 coulombs. There are 40 nucleons. Okay, within that, nucleons is a group term for protons and neutrons together. We've seen that they've got a very similar mass, so to three significant figures we can just quote the same number. So it's 40 times by 1.67 times 10 to the minus 27 kilograms, which gives us 6.68 times 10 to the minus 26 kilograms. Now hopefully you'll notice straight away we've not mentioned electrons here, and that's because you've got to look very carefully at what the question asks. It asks about the nucleus. There are no electrons within the nucleus, so we're simply looking at protons for charge and protons and neutrons for mass. So all we've got to do now is take our two numbers there and divide them. So it's charge divided by mass, And doing that gives us, for a calcium-40 nucleus, a charge to mass ratio of 4.79 times 10 to the 7 coulombs per kilogram. And an answer around 10 to the 7 is pretty common for a nucleus, so that's the sort of thing we would be expecting there. Example number 2 looks very similar on the face of it, but it is calculating the specific charge of a calcium 240 ion. Now that 2 gives us an indication of what the charge is. You might have seen that used in chemistry before, but a calcium 240 ion, the 2 bit means it's got a charge of +2, and the 40 tells us the isotope. Now it's an ion, so we're calculating a specific charge for the whole ion, not just the nucleus, so that's key. So the overall charge of this ion is +2. Okay, essentially what we've got here is the 20 protons in the nucleus, and we've got 18 electrons in the energy levels surrounding the nucleus. So we've got an ion, we've lost 2 electrons to give us that 2+. So the overall charge is simply 2 times 1.6 times 10 to the minus 19, which is 3.2 times 10 to the power of minus 19. So a considerably lower charge on the ion than we had on the nucleus in the previous question. There are 40 nucleons and 18 electrons. Now, to the number of significant figures we're working to, those 18 electrons are negligible. Okay, so we can make life a little bit simpler for ourselves here and just say, well, we've got the same mass that we had in the previous question. Okay, we've got 40 nucleons, which is 40 times the 1.67 times 10 to the minus 27. You can see on here we put the 18 electrons in there, but it's not actually made a difference to our overall value, which is still 6.68 times 10 to the minus 26 kilograms, the same as it was in the previous question. So the charge to mass ratio, again, just the 2 divided by each other, 3.2 times 10 to the minus 19 divided by 6.68 times 10 to the minus 26, and that gives us 4.79 times 10 to the 6 coulombs per kilogram. We've actually ended up with the same numerical part to that. That's just luck with what we've used, but it's the power of 10 here that's vastly different, showing the difference between specific charge for a nucleus, which will be an order of magnitude higher than that on a typical ion, which will be down at times 10 to the 6. Okay, so hopefully that just gives you an insight into doing that, shows that we can just ignore the mass of the electrons in most of these examples, unless we're doing something like calculating the specific charge of an electron, of course, which is something that you can have a go at the sheet. So do now have a look at those questions on the sheet. There's 10 specific charge questions to do, and then 2 slightly more advanced reworking ones, which we'll see if you can puzzle out yourself. So enjoy doing that, and do get in touch if you've got any questions. All the best. Bye.